Hello everyone, today let's solve the problem number 235, lowest common ancestor of a binary search tree. So what the question states here, so we are given a binary search tree BST and two nodes P and Q, right? So we have been given a binary search tree, means balanced tree, right? So binary search tree is balanced, right? So always balanced. So we have been given a binary search tree here and two nodes P and Q. You can clearly see here two nodes P and Q, and we have to find the lowest common ancestor, means LCA, right? So we have to find the LCA, means lowest common ancestor. The LCA is the lowest node in the BST that has both P and Q. So this definition, just keep in mind. I'll read this one again. This part is very important for this question. The LCA is the lowest node in the BST that has both P and Q as descendants, including itself. So this is very important, right? Again, I'll read. Just keep this in mind. The LCA or lowest common ancestor is the lowest node in the BST that has both P and Q as descendants, including itself, right? So I hope this is completely clear. Let's come to the first example here. We have 6, 2 and 8 here, right? So we have 6 to 8, 0, 4, null, null, 3, 5, right? This one you can clearly see 6280. Just give me a second here. Yeah, 62804 79 null null 3 and 5. This is fine, right? So the output here is 6. Why? So here the LCA, I mean the lowest node in the BST that has both P and Q as descendants here is 6. Quite obviously 6 here you can clearly see, right? This one I'm speaking of. Lowest common ancestor they have asked us to find. So this one 6 here in this case, right? So I hope this is clear. Let's come to the second example here. We have 62804 79 null null 35. So just give me a second here. In this case 2 and 4, P has been given 2 and Q has been given 4 in this case, right? So the lowest common the lowest node in the BST that has both P and Q, so here including itself, right, as descendants, including itself they have given. So for 2 and 4 the LCM here is quite obviously 2 itself, right? For the 2 and 4 the LCA is quite obviously 2 itself in this case. So the output that we need to return here is in this case is 2 itself. So they have in the explanation also they have clearly mentioned the LCA of nodes 2 and 4 is 2 here in this case, because node can be descendant of itself. So just give me a second here. 4 we have, 2 and 4 we have, right? So node can be descendant of itself according to the LCA definition. I have already read the LCA definition twice or thrice, right? So we know this part. So I hope the question is completely clear. What we need to do is completely clear as well. Let me clean this one. Let me clean this up. So just give me a second here. Yeah. First, let's discuss the approach, followed by the edge cases one by one, and then finally write the code and discuss the complexities for the code that we have written. Initially, let's discuss the approach first. So the first thing that we need to keep in mind here is binary search tree traversal, right? So the first thing that we need to keep in mind here is binary search tree traversal, right? I have considered the same example, the first example that they have given in the question, so that it will be easier for us to understand. We have already discussed this one, right? So P we have been given 2 and 8. So the LCA, so yeah, just give me a second. The LCA or the lowest node in the BST that has both P and Q as descendants here as 6, right? We already saw this one. We have already discussed this one. This is fine. So we are going with the binary search tree traversal approach. This is fine. Let's come to the step-by-step execution part. The same first example here. So here in this case, we will start at the root 6. First thing we have here is root node, right? So the root node, the value that we have at the root is 6. So we will start at the root 6. Since P is 2 and Q is 8 next itself, right? So we have 6, 2 and 8. I will not draw all the nodes here. I'm just writing here 6 to 8 here. Since P is 2 and Q is 8, both are on the different side. This is left subtree and this is right subtree, right? So since P is 2 and Q equals 8 are on the both sides of 6 here in this case, 2 is less than 6 and 8 is greater than 6. So 2 is quite obviously less than 6 and 8 is greater than 6. This ensures that this is the BST, right? Binary search tree. So this this one left subtree, the value of the left subtree has to be lesser than the this one root, and the value of the right subtree has to be greater than the root. So this is a perfect binary tree, right? In this case, so since p is 2 and q equals 2 are on different sides of 6, 2 less than 6 and 8 greater than 6, 6 is the LCA. We know this one, 6 is the LCA. So now the output that we got is 6 here, right? So the final output here is 6. The output that we got here is 6, and the output that I have mentioned for the first example is also 6, right? So both match here. Means this is equivalent. The output that we got is equivalent to the output that they have given for the example one. So the approach works absolutely correct in this case. Now we are completely familiar with the approach. Let's quickly discuss the complexities for the code that we have written. So not the complexity, sorry. Let's discuss the edge cases one by one. Sorry, this one, right? The first edge case here is both nodes are direct children of root. Both nodes are direct children of root here in this case. 6 to 8 directly, right? Both nodes are direct children of root here. In this case, the output will be quite obviously 6. We have already discussed this one, right? This is fine. Similar example we had already discussed. The first example, right? Let's move on with the second edge case. One node is the root here. One node is the root. So we have 2. We have 1 here, quite obviously. The LCA would be quite obviously this one. What do you call? 2 in this case, right? 2 in this case. So this is fine. We have already discussed the similar one. Let's move on with the third edge case here. Both nodes are in the left subtree. Both nodes are in the left subtree here, right? So here in this case, 6 to 8, and we'll consider 0, 4, right? Both nodes are in the left subtree here. You can clearly see both the nodes are in the left subtree. This one we are speaking of, right? 0, 4. So the output will be quite obviously LCA of these two nodes will be 2. This one, right? So here the output will be 2. So these are the 3 edge cases that we need to keep in mind, right? The first edge case is for both nodes are the direct children of root. Both the nodes are direct children of the root. So the second edge case is for the one node is the root, and the third edge case here is for the both nodes are in the left subtree, right? So these 3 edge cases that we need to keep in mind. Now we are completely familiar with the approach as well as the edge cases. As we are familiar with the approach and edge cases, it will be easier to write the code. Let's start writing the. So the first thing what we'll be doing here, we will loop until we find the LCA, or we will until we reach null, right? So for that one, I'll just be making use of the while loop here. While root not equal to null, inside the while loop, what we will do, first step here, we have to move left if both nodes are smaller, right? So we have to move left if both nodes are smaller. First, let's write the simple if condition here. If the value of p is less than value of the root, right? And same thing goes with the this one, value of q as well, right? So I'll just go with the ampersand here. This is fine. If value of q is less than value of the root, then here in this case, if both nodes are smaller, then we have to move left, right? So I'll just implement on this way. I'll just give here root equals root dot left in this, right? So this is fine. Let me make use of else if here. Else if both nodes are greater, then what we will do, we have to move right. If both nodes are smaller, then we are moving left. If both nodes are greater, then we will move this one, right? So I'll just copy the same thing and let me paste it over here. So here, what did I do? Just give me a second here. Else if I have given, let me do one thing. Let me type here p dot val greater than root dot val and q dot val here, value of the q greater than root dot val. So this is fine. We have to move right. So I'll just assign root to root dot right here. This is fine. So the next step or the final step here is, else what we will do, if P and Q are on the different sides, then we will just return the root. So in first example, we did the same thing, right? So here you can clearly see 2 and 8 are on the different sides. We returned the root, nothing but 6 on this case, right? So for that one also, we have to implement the same thing here in the form of code, right? So else I'll just give here return root. So this is it for the code. So the final step, we have to return one more thing here. So if P and Q exists in this one binary search tree, then this case will never occur. If not, we have to return null, right? So I'll just go with here in this case, let me return null. This is fine. So this is it for the code. Let me format the code once and let me hit the run button. Sorry. Just let's wait for some time. So you can clearly see here the sample test cases are getting passed. Means the code works absolutely correct in this case, right? So let me quickly hit the submit button. So let me quickly hit the submit button here. So you can clearly see here all the test cases are getting passed. Means the code works absolutely correct in this case, right? So let's quickly discuss the complexities for the code that we have written. So here the approach that we meant with here is binary search tree traversal. We know this one, right? So what would be the time complexity here? So it will be big of logarithmic n in a balanced binary search tree. Means nothing but height of the tree I'm speaking of. Don't get confused here, right? So it will be big of logarithmic n or log n in a balanced binary search tree, and it will be big of n in a unbalanced binary search tree. So for the worst case, it will be big of n. So let's consider the worst case here. I'll just go with here, or let me give big of time complexity would be big of n in the worst case, right? So what would be the space complexity here? The overall space complexity would be big of 1 here, right? So just give me a second here. It will be big of 1. Why it is big of 1? Because we are making use of the constant amount of extra space. Nothing but we are going with the iteration here, right? So we are going with the iterative approach. You can clearly see here. We are going with the iterative approach. So we are just making use of the constant amount of extra space here in this case. So overall space complexity would be big of 1 in this case, right? So the time complexity would be big of n, and the space complexity is big of 1 in this case, right? For the code that we have written. So I hope the complexities are clear, and I hope whatever the code that we have written is completely clear as well. For now, this is it. Thanks for watching, guys.